I'm not. I think for the people who stayed, we lost a few. We should provide at least one question for the final. There's two things I want to do. We never really got through looking at a couple of other systems for acquiring data that you might well come up with. And so I'd like to at least open those up a little bit. And the other is just something that's really interesting. It just has to do with another aspect of electromagnetic induction that you probably, you know about, but you don't really think about it within the context of the terms that we're doing and sort of the fundamental physics. So I think those two things are kind of interesting and make fill up the rest of the day. So just to refresh your memories, because we've been doing DC resistivity, but if we go back to inductive sources, then this was that EM31, had a little transmitter here, so it's just a little coil wire with current going through it, and then there's a receiver out over here, and we had brought it in and just sort of carry this thing around, and then you could have it so that it's standing up at hip length, or it could go down onto the ground. You could also turn it so that you have different orientations. So that's that was one thing, and then you've seen this a number of times. So that's just your apparent conductivity from the quadrature phase, and then your in-phase component. And this guy's basically a metal detector. So you see these blue spots in here, so that's telling you something about what's going on. And this is really apparent conductivity. And if you've got regions in here that are kind of uniformly resistive and it's looking the same in kind of both directions, then you're pretty confident you've got a 1D Earth, and maybe you've got something interesting there. When we did the very first lecture, we took you on this tour through Ireland, and there was one place that, or there was one case history that we haven't got back to, and I just thought it'd be interesting to do that. So they were looking for sand and gravel quarries. So now, actually, gravel is a commodity, right? And if you could find this, you might actually be able to make some money out of it. So the area is mountainous. It's got rolling hills and lakes, and it's basically glacial deposits. And the glacial deposits were what gave rise to the to sand and gravel. There's a lot of material that is boggish, sort of wet, sort of carbonate material, and that's very conductive. The gravel deposits, however, they're cobbles, they're stones, and they're resistive, so they have a low conductivity. The other physical properties that you might be interested in is the seismic velocity. So the gravels are really unconsolidated, so you'd expect them to have a really low seismic velocity. So therefore, you can think like a couple of different surveys, something to do with electromagnetics or something to do with seismic. So let's concentrate on electromagnetics. And there's a few things that were done. Again, from a reconnaissance viewpoint, something like the EM31 is pretty easy to acquire. You just basically go over this region with your EM31 instrument. You plot out the apparent conductivities. The resolution of this map is pretty bad, but you can still see there's red over here, right? So those are high conductivity areas. And then there's blues over here, which are low conductivity regions. So this is, if you're looking for sand and gravel, then these dark blue areas are what you're interested in. So that's great. That gives you kind of like a first order map of what might be there. And then you could use that map to say, no, I want to do a bit of a follow-up here, and maybe I'll just take a closer look at some of these regions in here. So that's what was done. That's what was done here. You pick up a couple of traverses that go through here, and then do a different kind of survey. And what they did was a DC resistivity survey. So that's one of the things that makes this particular case history nice, because we did the EM31 inductive source, got some reconnaissance. Now you follow that up with something that you actually put electrodes in the ground, and we're going to do a 2D DC resistivity, just the same as you had your quiz on. So when you do that, this is a cross section along one of these lines. So it takes the DC resistivity data, you generate these pseudo sections, and then you take those and you invert them, just as you were in this quiz, and you get a two-dimensional structure. You've got depth in this axis, horizontal locations on this axis. Again, the blue is resistive material, and the red is more conductive. So we notice these blue regions in here, which actually corresponds to the center part of these blues here. So now you've got two geophysical surveys. They kind of provide information about where that sand and gravel deposit is, and they sort of confirm each other. So that would be a really good type of survey. These other lines that are on here, actually that was the results from the seismic survey. These numbers are indicative of seismic velocity in kilometers per second, and that's basically 300 meters per second up here, and it gets down to a couple of kilometers per second down here. So everything is kind of fitting together. Low conductivity, low seismic velocity, and that would give you a good indication about where you should go and dig things up if you wanted to find that those gravel deposits. So that was case series that kind of tied in the stuff that we were doing. I mentioned that with the EM31 you could turn it on different angles, and the idea with that, all of these things always come down to the same thing. If I've got a loop that's sitting like this, then I've got a magnetic field that's going like that. If I make my loop in this direction, now I got a magnetic field that goes like this. These two sources excite the Earth in a different way, and if we did the sensitivity function for this, remember it kind of goes up and down like this, where this was sort of a normalized depth, and there was a particular depth at which we were most sensitive, but we're not sensitive to stuff that was right at the surface. This thing goes to 0. So it's a maximum. I forgot what this was, but it's sort of like z is equal to 0.4 or something like that, where that normalized depth is a true depth scaled by the distance between the transmitter and receiver. So that's what that sensitivity function looked like. When you turn this guy on its side, the sensitivity function looks like that. So now it's actually most sensitive to what's happening right at the surface. So that's good. So you can see, like, okay, maybe there's, just by taking the instrument, having it one way, and then tilting it, I'm going to get a different image out of what the Earth is like. Each of these data are going to provide more information. So that's the transmitter part of it. The other part of it is the receiver. So if I'm sitting here with a transmitter, and if I have a receiver that's oriented in this particular direction, then I'm going to get a certain signal. If I orient it in a different direction, I'm going to get a different signal. Each of those might tell you a little bit, slightly different information about what is really happening. And so the idea is that maybe you could go ahead and collect a number of different kinds of these data, and then get gradually build up more and more information about what's there. The other thing that you have at your disposal is the frequency. Because remember, the important thing about the frequency was that there was this skin depth, skin depth in meters, it's 500 times the resistivity divided by the frequency. So the higher the frequency, the smaller the skin depth. Or equivalently, if you go lower, then you're going to be able to see deeper. So you could imagine a system, again, the images here are pretty bad, but I'm not sure if you can see this. So there's a red coil here. This is called an EM34. This is, again, something that geotechnical and environmental groups would be using. It's got the following thing. So it's got a coil that's completely arbitrary. So you could do whatever you wanted with this coil. You could have it like this, or you could turn it however you want. And it's got a receiver, which is another coil that's sitting back here. And again, you could do whatever you want with this. So you could separate them by different distances. You could turn them in different orientations. They could be flat. They could be vertical like that. And each time you do something, time you make a measurement, then you're getting a bit of different information out about what's there. And you can imagine it. Eventually be able to put all that stuff together and get a good idea about what the conductivity is beneath the surface. There's kind of particular tuning distances that are good in this case. If you had a 6.4 kilohertz, then maybe you might want to be 10 meters apart. If you go smaller frequencies, then you might want to go farther apart. So you can gradually see how you could build things up. So this is often used for groundwater, mapping contaminants, and sometimes for just groundwater exploration for looking deeper. So that's an EM34. And okay. Then you have other guys too. This is another frequency domain system. It's called a GEM system. And this is more like it's kind of like your metal detector that you go along on the beach with. So there's a transmitting coil in here, and there's also a receiving coil. And it's operating at a particular frequency, and you can go over an area, and you could get a map out that looks something like this. In this case, he's looking for unexploded ordnance, and you get signals coming out like here that first order kind of are reminiscent of what we saw with magnetics and looking at the dipoles. So here's another frequency domain system. This one is actually, you're going to fly this one in the air. And it's something called resolve. You can kind of get a scale. So there's, 10 people across here. And this thing is called a bird. And inside the bird, there's this schematic that looks like this. We've got we've got pairs of coils. We've got a transmitter, and we've got a receiver. And these things are kind of matched. So you've got this transmitter goes with this receiver, ... And we've got some that are coplanar, and then we've got two that are vertical. They're sort of coaxial. So again, they will operate at different frequencies. 400, 6400, 100 kilohertz. Different frequencies see deeper. So the idea is that you collect enough of this data and you can kind of get a probing of what the near surface of the Earth is. So this is what it looks like. You're going to haul it out. You can put it on the top of your truck. And when you fly it, here's your helicopter, and here's the bird. And then they just fly this thing back and forth. Airborne acquisition is very efficient. It's costly with respect to the helicopter and stuff like that, but really you can acquire a large amount of data very quickly, and that's one of the reasons that these things are so popular. There's a whole other suite of data that we did not talk about, and that's called time domain electromagnetic data. And the only difference between time domain and frequency domain is in the transmitter. So in the frequency domain system, we're always thinking about putting on some kind of harmonic signal that looks like that. In time domain systems, the current source is often, it turns on and keeps on for a while, and then it shuts off. It's kind of like what we're doing in DC resistivity, but when we're working with electromagnetic induction, we're operating at very early times after that shutoff, and we can often get some kind of signature that's not related to the IP, but is actually related to the electrical conductivity. So that is probably 2 lectures all in itself, and it would do more harm than good to go into that, but I do want you at least to know that when somebody talks about electromagnetic systems, the systems that they're working with are either in frequency, or sometimes they're called time, the other ones are called time domain systems. And the basic principles are the same, but there's some details that change just because of the nature of the input waveform. Now, the last thing I wanted to talk about is just kind of interesting, but it's also quite relevant. Did I ask how many people have seen Northern Lights or Southern Lights? Oh, sort of half. And for those who did, what kind of displays did you see as far as colors or waves or any description? Green. So green, yeah. And where did you see them?
In Nunavut.
Ah, okay. As far up north. Who else has seen them? Where did you see them?
I saw a bit of green and purple up by Killam, Manitoba, near Churchill.
Okay, yeah. So these are all northern latitudes, and the understanding of why you see them at northern latitudes and you don't see them down here actually has to come back with the Earth's magnetic field, as well as how that Earth's magnetic field interacts with all of the particles that are coming from the sun. So this is a good schematic. So we got the sun. It's not to scale, of course. So we got the sun out here, and there's always these solar flares and eruptions and solar storms that occur on the sun. And basically what that does, it just spews out a whole host of charged particles. You got electrons and protons that are just sort of blasting out. Those particles come into the Earth's magnetosphere, and they interact with this. And the important, and perhaps the most important thing about the Earth having a magnetic field is that this magnetic field actually shields us from all these particles that come in. If we have a magnetic field, there would not be any life here. So you can thank the fact that you're here to the existence of the Earth's magnetic field, because what that does, these high energy particles that come in, instead of just sort of blasting through, kind of get deflected around. And so you could kind of think about us having a little bit of it's kind of like an umbrella around that just sort of protects us from all this stuff. And if you look at the magnetic field lines, you know, when we were drawing the magnetic field lines of the Earth, you know, we'd always sort of sketch things out, you know, that looks like this, right? And that is in fact what things look like when you're really close to the surface. But if you go farther away, then you suddenly find like, oh, things are really changed. And if you look at this picture here, you can see how that magnetic field is kind of blown back this way and kind of blown out this way. In fact, there is what's called a magnetotail that comes out here. This magnetic field comes way up there. So that's the static situation of the Earth's magnetic field and how it's protecting us. Despite the fact that this is actually acting as a shield, there are ways in which particles can sort of sneak through. They kind of go in through the back end here, and with field line reconnection, they kind of come back out this way. And as they come in, we have a charged particle. If you remember from first year physics, if you had a particle that was moving at a particular velocity, and it was through a magnetic field at some charge Q, there was a force on it that depended upon the cross product of the velocity and the magnetic field. What that means is that as these particles come through and they're interacting with the field, that there's a force that's acting on them that kind of controls how they move through here, and they end up spiraling down these magnetic field lines, so that the particles come in, they sort of spiral down, and then there's a region up at about 110 kilometers called the ionosphere, in which these particles actually move kind of horizontally across the, at that ionospheric level. So the particles come down, move across, and then they can go back up. Now, in doing this, we can imagine that we've got a lot of particles that are moving around here. Well, charged particle, that's a current, right? So now we've got all these currents that are flowing around here, and that is going to give rise to magnetic fields. Every time we have a current, we have a magnetic field. This region where the currents are trapped are called the polar cap, and there's a couple of main regions of currents called electrojets. There's an eastward electrojet and a westward electrojet, and all of this stuff is what is contributing to the northern lights or southern lights. I mean, do you know why we actually see anything? Why do we see particular color? Origin of northern lights or any of these? What's happening? Anybody?
Because they get excited and they certain frequency of energy.
Yeah, that's close. So if we've got an atom, okay, and then around that atom, so we got positive charges and neutrons in here. Around the atom, we got some electrons, right? Remember, there's these shells. First one has 2, next we've got 8, whatever. And the point about these shells is they're at different energy states. So if I have an incoming particle that comes in, so now I've got this proton or electron that's coming in, interacts with this guy, and if he knocks them out into an outer shell, so there's some energy that's gone from my proton to knock this guy out. Okay, that's good. But when he decays back, which he will, goes back here, and then there's a photon that's given off, and the photon gives rise to its color of a particular wavelength. So depending upon what the energy band difference is here, I'm going to see either a yellow or a red or a blue. Right? So how's this all working? So we've got particles that are coming in. We're kind of protected by our magnetosphere. Still stuff comes in. It's going through some regions in here through the electrojets. Those particles are hitting nitrogen atoms, oxygen atoms up there, exciting them. When those decay back, I get a color of light. So where is this auroral oval? It changes when there's a big storm. Here's a couple of pictures as a function of time of a big storm that occurred a number of years ago, and the color intensity here shows the magnitude of the currents that are going on. So you can see a couple of things. One is that the currents are increasing, and secondly, they're moving a bit southward. So that's just a kind of a bit of a blown up picture, and then this is what the resultant visual image would look like with these aurora. And for those people who haven't had a chance to see it, it's something you've got to do once in your lifetime, because they're just quite remarkable. You're just sitting there and you've just got these sheets of shimmering light that are coming in. And you just kind of imagine all these particles that are coming down and just creating all this stuff. It is quite magical. The thing I wanted to show you was the following. This record that we've got here, they have 3-component magnetometers, measure kind of an X, Y, and a Z as a function of time. So we've got time along here. And these are days. And and this axis is in nanoteslas. So we've got, a couple hundred nanoteslas through here, and you could watch any of these curves, and then all of a sudden you see something happen, and things start to fluctuate, and we get large changes in that field. Here's a blown up of that. You get, if you just look at, let's say, the green curve here, so it's green, and then it goes whomp down here, dot, dot, dot. So this is the magnetic field with time. So when I'm sitting up here, and 30 seconds later I'm down here, that's telling me that the magnetic field is changing a lot. Okay, so what is the first thing you think about when somebody tells you, oh, the magnetic field is changing? Anybody? Oh, I gotta do this one. Come on.
Inducing currents.
Yeah, exactly. I've got a magnetic field. I've got a time-varying magnetic field, right? So that means it's got to be generating currents in any kind of a conductor. So we can actually use that. This is actually great information to use to penetrate to find the conductivity way down deep inside the Earth. In fact, I did my master's degree on that a few years ago. But the other thing it can do is the following. We have, our whole power system is grids, right? So what do we do? We've got these electrical substations, and we have grids, that go along like this, right? And that's just a wire that's sitting up there. So now you can imagine you've got all these, got these towers, right? But they're all strung up with wires. And now if we took that and we put in some time-varying magnetic field, okay? So then, remember I've got my flux, which was the integral over the area, times b dot n hat dA. So in that case, this might just be the integral over the area of the BZ component. So whatever vertical component I've got. And that gives rise, that changing field, gives rise to a voltage. So my time rate of change of this flux gives rise to a voltage. So if you go back here, so at one point the magnetic field is like this, right? And just a short time later, it's like this. So there's a huge change in that magnetic flux, which means that there's got to be a voltage that's induced in this current, or in this wire. And if I put a voltage in that wire, I'm going to make a current. And if I've got a current on there that I'm not expecting, for these big power companies, I could blow a transformer. And that is exactly what happened. So there was a major blackout in New York. Your parents would know about this, you might not. There was the whole eastern seaboard was completely blacked out from power for a couple of days. And the reason for this was just these great big power grids, and they get this voltage that goes in. So you start to get these extra voltages and currents that come in, and they do have mechanisms. They try to shut things off, right? And they've got transformers that are things are grounded, and they try to prevent current from going. But you can get a power surge that comes through here, and that goes around that whole circuit much faster than you can switch anything off, and it does. Then those transformers, they just blow up like firecrackers. And that's exactly what happened. It just went around. It just blew everything up. So the point about this was that we actually induced, maybe these numbers aren't so important, but we induced these extra voltages and currents that just cause things to go up. So this is an entirely different application, if you like, but the physics is exactly the same, which is what I think is kind of interesting here. So you know something about the basic physics, and with that you're able to understand not only somebody going along trying to find a wire in the ground, but you can also understand, like, okay, here's the fundamental cause of a big electrical brownout in eastern Canada. Okay, so that was just something I thought you might be interested in. Wanted to show you that. And yeah, so what we're going to do then for the TBL on Wednesday, you basically write your own questions. So in each section, take a question, think of an answer, and then we're going to composite those. You'll get into your teams and you'll try to choose the best ones for your teams. And then we're going to look at those and put a couple of them on the final exam. And then Friday, party.